Okay, hello everyone. From my side, I'm Qian from the Institute of Concrete Structures at TU Dresden, and my college team has already introduced the ontology-based bridge component design. Now I will continue to another part of AI-assisted bridge conceptual design. It's a hybrid knowledge and learning-based approach to automated span planning, which is a critical step during the whole bridge design because it's connect analysis of boundary conditions to the following detailed designs of bridges. So before introducing this method, I would first like to clarify what bridge span planning means. In this work, span planning means deciding where to place the piers and abutments appropriate, and how to divide the total bridge into several individual spans according to series of planning rules from the standard and guidelines. So in our work, we firstly collect and classify these rules into two categories. Category A refers to topographic constraints. These are site-related boundary conditions. For example, the clearance requirements of the bridges with the crossings, different type of crossings, and also restriction of ranging piers in sensitive areas. Then the second category refers to the rules for span arrangement itself. For example, the span planning or the span layout should be structurally reasonable, symmetric layout, and so on. And also the span length should be within an economically feasible range according to our standards. For engineers, all these rules should be considered in the conceptual design phase. Usually they give some potential variants based on their experience and intuitions for the initial data or information from boundary conditions. Here, I would like to show examples with two variants. The first variant is, of course, rejected because the middle pier is located in the deep water area, which is difficult to construct and uneconomic. Then the second variant is also not reasonable because the middle span is smaller than the side span, which is statically inefficient. On the contrary, the third variant satisfies all these rules better and is therefore kept as the valid solution for the following or downstream design process. So in this work, the main research question is that how this span planning can be processed more efficiently with an automated AI-assisted method. Yes. For that, according to two categories of rules, we create a three-stage hybrid planning pipeline. The first step is to process the topographies, and starting from the 3D GIS data, as mentioned by Tim as well. We extracted the longitudinal profile along the planned bridge axis. This provides a basic topographic information. Then the second step is to apply rules in category A. With the help of ontology-based reasoning, we can simplify this longitudinal profile into one segment with the forbidden zones. It gives us a valid, simple design space. For the following, or the third step, we use the reinforcement learning to optimize and arrange piers. Now let's first look at the ontology used in the second step. Yes. The ontology we used in this work is bridge core ontology core, as also introduced by our ontology team. And relevant to this use case, and the main classes are shown here. Every bridge carries the infrastructure root, which is composed of a sequence of root points. These root points are subclass of location points and can be located in different zones like the forest, water body, taxation, and building. So because this ontology can be used for the reasoning, so the category A rules are implemented using SWARE, and then based on the specific bridge boundary conditions in bridge design project, the reasoners can derive the valid one with the forbidden zones where the piers should not be arranged. Here, I would like to show one example to clarify how it works. In this example, the bridge has crossed a waterway and a road. That means the clearance requirement should be considered. And then this profile is divided into a sequence of root points. and they are linked to the individual site-based zones like the open terrain, shore, river, and road. Then, based on the rules in category A, this profile can be classified into different parts. For example, the green part means the boats are portable, then the yellow part is not suggested but also portable, then the red part means that it should not be arranged. The pier should not be arranged, it's forbidden zones. So in this way, the complex boundary conditions can be converted into a simplified one-way sequence to any point of bridges representing the abutment and the blue forbidden zones. After the derivation of this 1D segments, now is the actual arrangement of piers and the span layout. Here, the reinforcement learning model will be already investigated and search for the economical and rule compliant arrangement using the rules in category B. Yes. The corresponding iterative optimization process are shown here. In each training episode of the reinforcement learning model, the starting point is the current planning phase with the pier position, span length, and unchangeable boundary conditions. The planning agents of the reinforcement model we analyze is the current state and decide the next actions to adjust arrangement. It could be, for example, the piers can be moved and the number of piers can be changed and corresponding span will be adjusted. After adjustment, the model will use rule in category B to check and evaluate them with the positive and negative reports, the penalty and rewards. And the focus here is primarily on compliance with the planning rules. Afterwards, the new state and corresponding evaluation will feed back to our agent, and this way the agent will gradually learn which adjustments or action strategies lead more effectively to the better solution. And after iterative optimization, the plausible span planning can be achieved. But due to them, here we skipped model training and the tuning of the hyperparameter for time. Then here I will show you one test demonstrations. In this example, we have for 1D segment for a collaborate with and then span and 35 meters. In this demonstration, we run the agent's 10 test rounds. And in this terminal, we can see that in each testing round, the agent will search for the appropriate number of piers and the position. Ultimately, the result is not a mathematically perfect solution, but it was evaluated by the rules, the agent, and the rule compliance solution. This can be seen here as well. So obviously, the model finds the value solution for this example, and similarly, we process the further testing round and testing. In this testing progress, we get also very high success rate. Yeah, after deriving the span planning, this will be integrated into our planning platform with this 3D topography that was developed by our project partner. Yeah, the last but not least, to conclude, our study presents a hybrid AI-based automated approach for bridge-span planning. In this method, the ontology-based reasoning defines the feasible design space, and the reinforcement learning will search for the span planning or the span arrangement more efficiently. And in the future work, we would like to plan to expand this model to handle more complex set conditions, and will integrate this hybrid method in an interactive large memory model powered platform to automate bridge concept design, not only the span planning, but also the cross-section designs of the superstructures. Yeah, thank you very much.